Hello everybody. Today we are going to study about chapter 3. This chapter 3 it is all about the three-dimensional coordinate systems, okay? And it also contain the knowledge about the equation of the line and the equation of the plane in that three-dimensional space, okay? So for the first clip we are going to talk about the section 3.1, which is the introduction on the three-dimensional coordinate systems. Okay, so let us first talk about the point in space. Previously what you have learned is the point in the two-dimensional space, which is the typically the x is the horizontal axis and the y is a vertical axis, and this x and the y, okay, is a coordinate along the horizontal for x unit and along the vertical by y unit, okay? So that will be your coordinate x and y. However, in the three-dimensional space, the coordinates, okay, of the point require three numbers. Let's say x, y, and z, like this, okay? So to represent the point in the space, we are going to fix the so-called origin again. Same thing as in your two-dimensional space. Okay, we are going to have the origin. So now the origin is 0, 0, 0, which is usually called the point O. Okay, and also the coordinate axis. Okay, which will be now the x, the y, and the z. Okay. So in terms of three-dimensional space, okay, usually we'll write this way, that your x will be the one over here. Okay, this is the x-axis, and then the y-axis will be the one over there, and the z-axis usually is the one that is pop up from the floor. So we are going to think of this one, the xy plane, as a floor, okay, and there will be several plane. For example, this one, the one that according to the x and the z, it is called xz plane, and this one, the one that belong to the y and the z axis, it will call the yz plane. And actually there are typically the equation of each of the plane. We are going to introduce the easy one first. For example, the one on the floor, which is the xy, so it means that your z always 0. Okay, so we didn't see the z, so the z is 0, okay, right here at this level. And then for this one, the xz plane, then it means that your y is also 0, okay, over here at this level. And then for the yz plane, it means that your x is 0 over there. Okay, so this is the plane that is according to each of the axes. Okay, so each of the axes will be so-called orthogonal. So the orthogonal, it means perpendicular. Okay, same thing. Okay, sometimes it's called perpendicular, sometimes it's called orthogonal to each other. So it is the right degree angle. Okay, so it's just like this. And actually the way that we represent the x, the y, and the z axis will according to the right hand rule, as you did in physics. Okay, so the point ABC right here, okay, the point ABC right here is going to be the point on three-dimensional space, okay, that is going along the x-axis by a unit, okay, over here, this is a unit, and then going along the the y-axis for b unit. Okay, so as you try to project it on the floor first, so here's the a and the b, and then it is elevated up along the z-axis by a c unit. Okay, so it is right here, here's the z-axis. Okay, this is one of the point ABC, and then the plane that is parallel. Okay, so remember the plane, for example, the one on the floor, the xy plane, which is called z equals to 0. So if you elevate this plane up, okay, and here is your K3, this level, okay, the plane just elevate parallel to the floor. So this one is so-called the plane Z equals to K3, okay. On the same token, if you're talking about this plane, okay, this one is the XZ plane, or it is called the Y equals to 0 plane right here. And then you translate this one over there to this level for at K2, okay, intersect your Y axis at K2. So this plane now is called Y equals to K2, okay. And of course, if you talking about this plane, the one according to the Y and the Z axis, which is X equals to 0 plane, and then you just pull it out, okay, pull it over here to this level at K3. So this one is called the X equals to K3 plane, okay. So the Z equal, it will be the plane that is parallel to the floor, which is the XY plane, okay. And the Y equal will be the one that is parallel to the XZ plane, okay. And this one, the last one, X equal, will be the one that is parallel to the YZ plane. So can you see something special on each of them? For example, the one with Y equal will parallel to the plane that has no Y in it, and the one with Z equal will parallel to the plane with no Z in it, and then here the one with X equal will parallel to the plane which has no X in it, okay. So it look like this. So it's just a plane or a straight sheet of paper, okay. Now the one that you are going to need is a distance formula, and the distance formula, it is simply using the Pythagorean theorem, okay. So for example, if this one is the point x1 y1 z1, and this one is the point x2 y2 z2, now what we can find is this diagonal on the floor first, okay. So let us determine the axis to be like this one is x, this one is y, this one is z, okay. So the displacement along the x-axis, okay, from this point x1 to the point x2, the displacement will be x2 minus x1, and then the displacement over here along the y-axis will be the y2 minus y1, and actually they are parallel, okay. These two, they are parallel, so it means that the red one over here, it is the hypotenuse. So by using a Pythagoras theorem, this one, it is x2 minus x1 square and y2 minus y1 square added together and then taking a square root, okay. After that, we are going to look at this right triangle instead, okay. This one is another right triangle, okay. The red one is already shown by using a Pythagoras theorem, and the blue one here, it is elevated up from the floor, I mean not the floor, from z1 to z2. So the displacement will be z2 minus z1. So again, this one is the hypotenuse, so it will be a square root of the red square, okay, this one square. So it is x2 minus x1 square, y2 minus y1 square, and then added the another leg of your right triangle. So you got z2 minus z1 square, taking a square root, okay, because we are using the Pythagoras theorem again. So just simply saying that the distance between 2 points, okay, P1 and P2, finally it ends up with the difference between each of the coordinates square, you see, and then you add them up. After that, taking a square root, okay. So don't forget the last one, the taking the square root thing. All right. And actually, I mean, because you got a square on each of the difference, so actually you can use either x1 minus x2 or x2 minus x1. It doesn't matter. Okay, it will come back to the same thing after you taking a square. All right. So this is one of the things that you may need to know. After you got the distance between two points, okay, in the three-dimensional space, then the thing that you can define immediately is the equation of the sphere, because as you remember, the equation of the circle, it is all the points, right, that contain the same distance from the fixed point center, like this. So this one for the sphere, it will be all the points, okay, in three-dimensional space. That is again has the distance, fixed distance r from the fixed point center C at HKL. Okay, so let's say that here is the point x, y, z, okay, on the sphere. Then it means that the distance between this x, y, z and HKL, it is a fixed r. So actually at first you are going to take a square root, remember? Okay, you are going to take a square root, and then the square root of each of the component, okay? This was the first component, the second component, and the third component in the coordinates. So you have a difference between the first square, difference between the second square, the difference between the third square, and then it must be equals to the same distance r, okay? However, if you keep the square root like this, usually is not really common to keep a square root like this. So what we did is to square both sides. So it means that the square root is out, and then after you square it again, you got the r square. Okay, so don't forget that on your right hand side it will be the radius square. Okay, so the r is the radius of the sphere. Okay, so right now is some example. Okay, after we have go through some basic concept of your three-dimensional space. Okay, so first you need to sketch the point 0, 5, 2. So let's call this what is a P1. So what we are going to do is to write the coordinate system first. So the one that is going up, let us call the Z, and then this one, the one that look like is come out from the paper, it is the X, and then this one is a Y. Okay, so this point means that your X stay at 0, but then your Y go to 5. Okay, so this is the one of the place, okay, for 0, 5, and then it is elevated up by 2 units. Okay, so here is 2, so this is your P1, which is 0, 5, 2. Okay, so the second one, the P2, let's say you got a 4 along the X. Okay, so let's say that here is a 4, and then a 0 along the Y, so it just stay right there, and then you go down by 1 unit. So let's say that your Z continue down, so here is by 1 unit. Okay, so it is -1, so there is your P2 right here. Okay, how about what if you need to go like 2 on the X, so it's half of this, 4 on the Y. So you got this projection on the floor first. Here's a 2, there's a 4, and then you elevate it up, okay, parallel to the Z-axis by 5 units. So you got your P3 at 2, 4, 5. Okay, at 2, 4, 5. Okay. What if your P4? Okay, it is going along the x-axis by 1 unit, and then continue by going on the negative y-axis for another 1 unit. So it go like this, okay, and then it is elevated up again to the 2. So here it is a P4, which is 1, -1 and 2. Okay, I mean, you guys are engineers, so you know how to do a drawing very good, right? So you should be able to draw this three-dimensional space and determine each of the point very easily. Okay, how about this one? If we need to sketch the surface, okay, which is represented by this equation. So actually, if I mean, later on you are going to know that this equation, this surface is actually called a plane. Okay, so the plane is just a straight sheet of paper, is like a sheet of paper, okay, has no curve. So this one, let us determine the z-axis, the x-axis, and the y-axis, like that. Okay, and this one, there's no z, so it means it just simply saying that your z can be any number. Okay, so you are going to concentrate on the x and the y first. So if your x is 0, okay, it look like you draw a straight line on 2-dimensional space. If your x is 0, your y is 1. If your y is 0, your x is 1. So here is that straight line in 2-dimensional space. But it's saying that your z can be anything. So this straight line is look like a scroll of paper. So you are going to unfold the scroll, okay, and then just put it as a big sheet of paper like this. Okay, it can go all the way up or all the way down. Okay, it doesn't matter because your z can be anything. So this is the plane that is so-called x plus y equals to 1. So it determined, roughly speaking, by these 2 points, okay, on your x and y. Okay, and it looked like a big sheet of paper, okay, that is scrolling along this line. Okay, so you're going to unfold it, okay, as a straight sheet like this. Okay, now if you need to know whether the triangle with these 3 points are equilateral or not, okay, you are going to say that I mean, because you got 3 points, okay, so you can find the distance between PQ, you can find the distance between PR, and of course the distance between Q and R. And then what you are going to do is to check whether they are all equal or not. If they are all equal, I mean the same sides, it's going to be the equilateral triangle. So let us first find the PQ using a Pythagorean theorem, right? This is very easy. You can do -2, -1 square. So this is a difference between the first coordinates, and then the difference between the second coordinates, and the difference between the third coordinates square, taking a square root. Okay. So the rest it just for you to have a good calculation. Okay, so this is a 9, this is a 4, and this is a 1. So it is a square root of 14. Okay, now the second one, let's say a PR. So it is a square root of the difference of the first component. So take a look carefully. This is -2 minus -1. So it is a plus again. So you got a square. And then 4 minus 1. And then a 0 minus 2 for the last component. Okay. So what you end up with is a 1, is a 9 again, and it's a 4. So of course it is a square root of 14. How about the last one, the QR? Okay, it is a square root of the difference of the first component. So here it is, the second component, and of course the third component. Okay, so the first one will be just simply 2. So you got a 4, you got a 1, and you got a 9 again, you see. So it is a square root of 14. So because they are all equal, so it means that the triangle consists of these 3 vertices. It is a equilateral triangle, okay, because all the side of the length of each side, they are the same as a square root of 14. Okay, now if you need to find the equation of the sphere, so the equation of the sphere is what is x minus h, y minus k, and z minus l square equals to the radius square. So if everything is already determined, so you got the equation of a sphere to be x minus 2, y minus 1, and z minus negative 1. So it is z plus 1. And don't forget, here is a 4 square, okay, not only a 4. And you need to find the intersection, okay, of this sphere with the xz plane. So what does the xz plane mean? So which one is missing? Your y is missing, so it means that your y is 0. So the intersection with the xz plane, so it means that if your y is 0, what happened? So you got x square, x minus 2 square. Don't forget that only y is 0, so you got 1, and then you got the z plus 1 square, of course, and this is 16. So it means that you've got a smaller circle as your intersection, okay. So it's simply a circle, okay, at the center at 2 and negative 1, and then the radius is a square root of 15. Okay, how about this one? You need to find a equation of the sphere that's passing through the origin, and the center is 3, 2, 1. So what you don't have is the radius, right? So you can find the radius because it's saying that the sphere is already passing through that origin 0, 0, 0. So it means that the distance between the center and the origin should be your radius. And what you can do is to find a square root of 3 minus 0 square, 2 minus 0 square, and 1 minus 0 square, and taking a square root. Okay, this one will be, of course, a radius. But if you need to find the equation of the sphere, you should know that it's going to be, of course, x minus 3 square, y minus 2 square, z minus 1 square equals to the radius square. So why bother taking a square root, okay, to find the radius, right? So you can just ignore the square root and then simply just find the radius square at once. So here's a 9, a 4, and a 1. So your radius square, it is 14. Okay, so that will be the equation of your sphere that you need. Okay, so we are going to stop this video clip at this point, and then the next one we are going to talk about the vectors in 3-dimensional space. So you may need to go back and review yourself about the vector on the 2-dimensional space that you have learned before. We'll see you on the next clip. Bye bye.